Hello.
Welcome you all to the day 2 of BRICS conference. Today's first talk will be introduced by Professor Ya-Xiang Yuan. So I invite him to introduce the speaker.
Oh, thanks.
Okay.
Hello. Yeah, it is my pleasure to introduce my friend Yuan from Chinese Academy of Sciences. And Yuan is one of the tallest mathematician in optimization theory. And he is the president of International Council for Industrial and Applied Mathematics. So without any more addition to this, let me invite Yuan to give the talk on list S2 null, updating quadratic model for derivative-free cross-region algorithms. Yuan.
Okay, thanks so much. Thank you for the introduction. Thanks, Mr. Chair. Thank you, Raj, for your introduction. And also, I want to thank the organizing of the conference for inviting me to give a talk at this important BRICS mathematical conference. So I'm very happy to be at the conference, but it's a pity due to the COVID-19, the virus, I cannot go to India. I mean, India is a country which I look forward to visit, but not yet be able to go. So today I'm going to talk about a work which is actually joined by one of my students, Peng Xie, is about this H2 norm updating quadratic model for derivative-free trust region algorithm. So this talk basically will be dedicated, I want to say this talk is dedicated to my PhD supervisor, late Professor Powell, who has made tremendous contribution in the field of optimization. I mean, nowadays, machine learning, AI is very popular, and most of the key technique for AI and machine learning is statistics and optimization. And Mike Powell, he has made a great contribution like augmented Lagrange function and Cauchy-Newton method, and also derivative-free method. That is the topic I'm going to talk today. So the outline of my talk is, first of all, I will give a brief introduction about derivative-free optimization, and then I will move to our motivation, how we study this H2 norm updating quadratic model for building optimization method for solving optimization problem without using derivative. Also, I will give you some implementation detail about how to implement our algorithm, some of the computation technique to make the algorithm efficient and also stable. Finally, I will give some numerical results and also a short conclusion at the end. So let's start the introduction part, which is about really a brief review of derivative-free optimization. As I said in the beginning, optimization is getting more and more important in scientific computing because of nowadays machine learning and artificial intelligence, and also these kind of popular practical problem are the core of them optimization. So today I'm actually talking about the very simple unconstrained optimization. Namely, you minimize the function f in the whole space. Here, I think I'm talking about the real Euclid space, which have a finite number of variables. So the number of variables is n. So the type of method I'm going to talk is about derivative-free method, which means we don't use the derivative of the function, only use function value. That is the free mean. I mean, we don't use derivative. The advantage of this such kind of method is because we don't need derivative. That means those methods normally is very simple and quite easy to implement. All the iteration is based on function value. And think about it, you have a practical problem, you only compute the object, then you can move and find a new point. And even though it's simple, but such kind of problem have a broad application. Many of the real world problems can be modeled as kind of optimization problem where you don't have gradients or derivative. Either the gradient are not easy to compute, or sometimes it's impossible to get. Some of the like black box optimization, really you don't know the function. Sometimes you don't know how to write down the analytical form of the function. You just have input, you can get output, then you can compute the function by some kind of simulation. But you don't know, I mean, the analytical form. That means you can't do the derivative, I mean the gradient operation. That is the advantage. You have broad application. But the same things which give us advantage and also give us disadvantage, because we don't have derivative information. That means it's not easy to get a good approximation to the original function using approximation model, because if you have a higher order information, we're easy to get high accuracy approximation formula. But only function value, that means our approximation is not easy to get to high accuracy. A lot of things, I mean, computationally, I mean, even though we're easy to do, but we do theoretical analysis because we don't have much to play with, because we don't have gradient information. That means it's very making our theoretical analysis is very complicated. As I said, derivative-free optimization has broad application. Here I will give you a few examples. For example, the tuning of algorithm parameters itself is a kind of derivative-free optimization. Thinking you have an algorithm, they have some parameter you have to adjust. I mean, basically, I mean, the parameter will affect efficiency of the algorithm, but you don't know the function. So then you can only do the test, and then you can, the tuning of such parameter is the kind of derivative-free optimization. Also, optimal design problem in engineering design, such as wind platform design, acoustic shape design, or hydrodynamic design. Such kind of engineering design, lot of such kind of design problem is actually the optimal design is also a DFO. Also in biochemistry, molecular geometry, I mean some of the structure like protein folding, this kind of problem is also derivative-free optimization problems. Also automatic error analysis it also can be modeled as a derivative-free optimization, such also as dynamic pricing in economics or finance, and also integrate circuit design, also another example. There are a lot of derivative-free optimization algorithm available, so I will give you a very brief, I mean, not comprehensive review here. For example, line search type method. I mean, just the straightforward one is alternating coordinate. Think about it, you have 100 variables, then you fix 99 of them, and you just adjust one of them. Then you get a new point. Once this is fixed, you choose another one and moving in the other direction. This idea can generalize not in the variable direction. You can actually rotating the coordinate. That is the rotating coordinate. Also can be generalized to pattern search. Also use line search is conjugated direction, where you can using iteration information to construct direction which conjugate each other, assuming the function is quadratic. In the line search type class method, they also including finite difference cosine Newton. Even though you only have function value, but you use finite difference, you can get approximation to higher order information. And also you can generalize line search idea to other type of method. Another big class of method is called the direct search method, such as the simplex method. Basically, you in the n-dimension space, if you have n plus 1 point, which will have a kind of simplex, then you can compare the value higher or lower in this simplex. You can making the simplex, either reflection or enlarge or shrinking in this kind of that have originally can trace back little mid method and also modified simplex method. The simplex type method can also generalize to directional direct search method, such as generating set search method. And also in this class, we have mesh adaptive direct search method. Another type of method is called a model-based method. This method is really closely related to the method I'm going to report today. The idea is you build a model to approximate to original function. Then you're trying to minimize the model instead of original function. And hopefully you will get a better approximation point to the solution of the original point or original problem. This type of method, of course, you can use in polynomial model, such as linear model, quadratic model, and also Powell use so-called underdetermined quadratic interpolation. And also other type of polynomial, you can use the regulation idea to make the model more accuracy. Another type of function is using as the radial basis function, not the quadratical base. There are also many other types of methods, such as hybrid method, like implicit fitting adaptive regularized method, or some kind of heuristic algorithm, like simulate annealing or artificial neural network, or genetic algorithm. Also like Bayes technique, also other type of statistical idea can be used in optimization. Actually, statistical optimization are closely related. That is more or less a kind of very brief review of algorithm for delivery optimization. If you want to know more detail about delivery optimization, there is a very good book by Andy Cohn, Katia Scheinberg, and Louis Vincent, published about 10 years ago by Siam, which is called the Introduction to Delivery Optimization. In particular, I want to say a few words about the Powell's quadratic approximation algorithm, because that is the method I'm going to talk today closely related to. Powell's main idea, giving a function which you know only a few function values, you don't have gradient. So the idea, Powell's idea is how I can build a very good model, which is closely or accurately approximate to the original function, using only function value. One straightforward idea is use quadratic approximation. So Powell used underdetermined interpolation. Think about the quadratic function in n-dimensional space, which you have the function value, which is 1 parameter. You have the gradient, which is have n parameter. You have the Hessian of the quadratic function, which is half n times n plus 1. So totally, a quadratic function should have freedom of half n plus 1 times n plus 2. So when n is very large, then this is really too many parameters. So that's why Powell used underdetermined interpolation. If you use underdetermined interpolation, that means you have fewer interpolation points. That means you have a lot of freedom. So the quadratic model have a lot of freedom. How you update the quadratic model? So Powell saying, I built the model updating from the previous model. So thinking about yesterday I have a good model, today I use a model which should not be too far away from the model I used yesterday, something like that. And that's the idea of Powell. And also once you build the model, then you can minimize this model to get the new point. The minimization is done in a trust region. That means I don't care because the point which is far away from the current point, the minimization is only in the local neighborhood. Powell actually has developed a series of software for solving DFO. I mean, here I give some of his software here. The last one is actually can solve linear constraint problem. Powell's software recently have been maintained by one of my former students, Zai-Kun Zhang, who is now a professor in Hong Kong Polytechnic. Last year, he has maintained Powell's software, which can be downloaded from the internet. So I will give you a roughly idea how trust region work. Think about, I have 5 points, which x1, x2, x3, x4, x5. So that is in a trust region, I call it a region, which is now I draw in the red circle inside this ball. So you're trying to build a model in this ball, use this 5 points. So I minimize this model, so I will get, possibly I will get a new point, which I call x6 or x-opt, because that opt means the optimizer of the model. So now I get an additional point. We assume this point is a good point. So that means now in the next iteration, I will move to the center into this new point because I get improved. So in this new point, x-opt, now I'm centered in this new point. I have a new trust region ball. So I'm thinking about the problem. I'm moving from one point to the last point, have a new ball. And in the ball, I have a model. I minimize the approximation model. In that way, hopefully I will get the minimize of the original function. That is the trust region approach to the derivative-free optimization. So as I said, Powell used underdetermined quadratic model. Think about it in one dimension, you have only 2 points. So I have draw a line which is cross these 2 points, which is the linear function. But for quadratic function, you can add any blue point, then you can get a different quadratic function. That means you have freedom in choosing quadratic model. Powell's idea is because I use underdetermined quadratic model, I have freedom. That means I can choose the best quadratic model in some sense because I have freedom. Once you have freedom, you always ask yourself a question, which is the best choice? So now go to Powell's way of choosing quadratic model. Powell obtained his quadratic model by minimizing the distance of the Hessian of the quadratic function of the current iteration to the previous Hessian. So that is, I write down this formula here. Of course, subject to the interpolation condition. X, the quadratic function have to equal to the function value at a set of points, which is Ck. The number of points in this interpolation point, as I said, is greater than n plus 2 and less than half n plus 1 times n plus 2. Because for the full interpolation, you would require n plus 1 times n plus 2 divided by 2. So because they have the freedom, the minimization, that means they allow you choose this quadratic model. Then Powell's model is based on this optimization problem. Of course, there is other way of to choosing the quadratic model. As I said, the quadratic model is not unique to satisfy the interpolation condition. The different way is by replace Powell's object by other object function. Here I gave three different choice. One is by Kohn and Toyndt, and another is by Kohn, Scheinberg, and Toyndt, and another is by Bandler, Scheinberg, and Vincent. They have different way of choosing. So I want to remind you, because later on we will go to our algorithm, because Powell is trying to minimize the distance of Q and Q minus 1 of the second order derivative. Kohn and Toyndt minimize the Hessian and also the gradient. And the Kohn, Scheinberg, Toyndt minimize the Hessian itself. So think about all this minimization is trying to minimize either the distance or the second order term or the first order term. No zero order term is in those optimization. Why? Because the zero order term, the function value term, because we have the constraint, the interpolation condition, because the function itself, you are using the interpolation because, so we're thinking, we're assuming we have a good function approximation. So what we care about first order gradient and or second order gradient, because we don't have those information. That's why Powell and also Kohn and Scheinberg, these people are thinking about this norm in minimization. So the way of Powell's idea is very clever, because look at this triangle, which is basically the Pythagoras theory. So you try to minimize the distance from QK to QK minus 1, which is QK is the projection from QK plus minus 1 to the space, which satisfies the interpolation condition. So think about this backline, the solid backline, which is all the quadratic function which satisfy the interpolation condition. So QK plus 1 is kind of a projection point. So look at this picture, we'll see the distance from F to the quadratic function QK. I mean, if we measure in this second order term, second order derivative term, then the distance from F to QK is, of course, will be shorter than the distance from SK to K plus 1 and minus 1. That is the improvement. So that means we have a good approximation property of Powell's model. Indeed, theoretically, if we're assuming we have enough interpolation point, then we can prove Powell's model is a fully linear model. I mean, which satisfies the following two inequality. So you can see the function value approximation will be to the order of, to the square of the distance of the charge region ball. And the gradient accuracy will to the linear order. So that is the kind of really good approximation. So function value to the second order accuracy and the gradient to the first order. So the question we want to ask, whether it is possible we can build even better quadratic model than Powell's model, because the Powell's model is widely regarded one of the best one and seems, I mean, computationally is the best derivative algorithm for solving an optimization problem without using derivative. So that is our motivation to study this problem. So now I give you why we are proposing or using least H2 norm updating quadratic model. So this is back to our motivation. I want to go to some more old results. Think about a quadratic function in n dimension, which have the Qx. If Q is the quadratic function, we can write down the second term I mean, the Hessian is capital G, and the gradient is a small g, and the constant is g, if we bound this quadratic function at the point x0. A very interesting and important result was obtained by one of my former students. Actually, he did this result when he was my PhD student more than 10 years ago, about 10 years ago. So he proved a very interesting result that if you're trying to minimize this quadratic function, the Hessian, the normal of the Hessian plus the normal of the gradient, that is the kind of you're trying to minimize the normal of the quadratic function to some sense, which will be equivalent to minimize the H1 norm of this function in the trust region ball. So that is very interesting because the first P1 problem is just minimize the quadratic function within the interpolation condition. But the second problem is minimize a kind of norm in the trust region ball. Of course, the radius of the ball have to be in some collection, I mean, with the weighted number sigma in the first problem. That is a very interesting problem to build a bridge about, I mean, thinking about the interpolation in certain property of the quadratic function, which is equal to a special mathematical norm of the function as theoretical. So that is inspired us to consider a different norm, what we call the H2 norm. The H2 norm we define is 3 terms. One is L2, another is H1 of, I mean, which is depend on the integrate of the gradient, and also the H2 in the later in the older definition of H2 is actually the second order term, the integration, the mean value of the integration. So that is our definition of our H2. So there is 3 terms. So maybe I should use, because the confusion of the 2 H2 here, the last H2 here is showing the standard textbook H2, and my definition of H2 is really the combination of first order, second order term, and the third order term approximation. This is also, we're trying to build a quadratic model, which is a minimization similar to Powell's idea. We're trying to minimize the H2 norm in the trust region ball. Within this H2 norm, within the interpolation condition. Similarly, we can prove these have the Pythagorean trigonal property, either the projection, and then we can get the reduction, get an improvement of the approximation of the function. The ideal proof is very simple. I'll not get into detail. Basically, thinking about it is a projection, then all the other proof is very simple. The advantage of H2 norm, then Powell's original norm, is because first of all, we were able to using the projection, the H thing. More important, using the H2 norm, we can relax the minimum requirement for the interpolation point. If I remind you, in Powell's algorithm, we require the number of interpolation points to be at least n plus 2. Why? Because Powell's idea is, or all the previous quadratic model, the idea is using interpolation to get good function approximation. We use the other minimization to get the gradient and the second order information, high accuracy. But if we use H2 norm, because the H2 norm itself contains an L2 term, which is control the error in the function itself. Look at the last line in this slide, the last term, which showing if we have good accuracy of the H2 norm, then the last term will control the function value itself. If the function controlled well, that means we don't require so many interpolation points. So that means we can relax this condition of m greater than n plus 2. I think have this idea, that is the main idea of our technique. I mean, the rest is more theoretical, maybe boring to you, but nevertheless, I will go to some of the results. First of all, we have some theoretical results of showing the function bound by the H2 norm. That means the function itself, the gradient, can be bounded by the H2 norm. The idea for using the proof is by the two important inequality. One is the Morris inequality, another is the interpolation inequalities. Those is more, I mean, function analysis results, which is straightforward. I will not go into detail. Having this, we can get the approximation bound for the H2 norm, which I can get in the trust region ball, the function approximation, the gradient approximation, which will be very similar to the full linear model of Powell's result. That means if we use this H2 norm update, we'll be able to improve the accuracy of the approximation from case iteration to the K, from the K prime minus 1 iteration to the case iteration. That means the norm will get reduced, and hopefully we can get a conversion. Of course, this is not a rigid proof. It's only a kind of intuitive. If we have this algorithm, very likely we should have this result. But that is not I have to admit that is not a strict proof. First of all, I can give you a very simple example. Think about the function which is have the value equal to 1 at the original point and are zero at all the other whole 2 by 2 plane. And if we use 3 interpolation points, then I compute the least formless norm, F norm, and also compute the least H2 norm. I mean, the F norm minimization is plotted in green here, and the H2 norm is plotted in blue here, and F is originally a function. So you can see the blue function is much closer to the red function than the green one. So that means for this particular example, we can see the H2 norm is really can improve the F norm. So now the rest is the way we can show some theoretical results about this H norm updating quadratic model. Actually, for theoretical analysis, I can make it more general. So the H2 norm now I can make it more, I can call it a general H2 norm, because I really a kind of weighted mean of these 3 terms instead of just the 3 adding themselves. I can also have the similar result. I can also get the H2 norm for the quadratic function, which is have a very explicit form, even though it looks very complicated, but they have analytical closed form formula to compute. So give a quadratic function, you can compute the 2 norm in the ball, in the trust region board in an analytical formula. And the subproblem I have to solving to minimizing the least H norm is a very simple quadratic minimization within linear constraint. So it's a very simple problem, even though I have a lot of terms, but basically the simple problem. I can give you some of the detail of the algorithm. For example, the coefficient you can compute. Of course, in my implementation, we are considering the special case of all these constants are the same. Solving this subproblem is very easy, because write down the Lagrangian function and solving minimize this Lagrangian function, or setting the stationary point of the Lagrangian function. So the KKD condition will have these 3 equations. Using some reformulation, in the end, you can get the linear system for the KKD system. So that means in the end, we can solve in this linear system to get the lambda C G T. T is the definition given in the first line of the slides. Once this the needed system is solved, we can get the capital G, which is a quadratic term. In that case, we can get the quadratic function. The detail I'll not go to boring you in the detailed computation, but that is what we need to implement our algorithm. So actually, Powell's algorithm, the least F norm, is a kind of special case of a general norm case. Just C1, C2 equal 0, and C3 equal to 1. Now, I will go to some of the implementation detail of our algorithm. First of all, I said that KKD system, look at the KKD coefficient matrices, which is well structured. And moreover, the structure of the method, in each iteration, we have to update the KKD matrices because for doing theoretical analysis, we need to get a general result about the matrices. If we take one row and one column and replace by a new row and a new column, we can quite easy to update the inverse of this matrices. Then we can easily to do the computation. The ideal proof is constructive. I'll not go into detail. You have to trust me about my formula. If you are suspected, you can get a copy of my paper. Of course, in the algorithm, we're actually not the P and not the Q, but it's actually the same column and the same node, which is a special case. That's what we use in our algorithm. So having done this, that you know the inverse of the KKD matrix can be easy to update. That means we can compute those parameters. Once we compute this parameter, we can get the model. Another small point I have to mention is also about the implementation detail and about how makes the algorithm more stable. Because look at the update formula. We have a term which have a denominator, which is right down here. And we can try to maximize the denominator, so make the algorithm more stable. So that means they have choose the new point, which is shift away from the X operator, then to get a better point, then to make the algorithm stable. That is somehow some of the details of the algorithm. Now I will very briefly tell you some of our numerical tests. Before doing the set of the numerical test, I show you a very simple illustration, an example. Look at the function, a quadratic function, x squared times y squared plus x plus y plus 1. This is, this is a very simple quadratic function. So I use in 5 points, given in the box here, the 5 point, x1, x2, x3, x4, x5 as interpolation point. Use these 5 points as an interpolation condition. You try to minimize a quadratic function to f, either by the least f norm or by the H2 norm. The least f norm, the solution is HQ1, and the least H2 norm is Q1 bar. So we minimize this approximation function, Q1 bar, which we get X operator. And we minimize the H1 bar, we get X operator bar. So the distance from the X bar operator to the solution of F is much closer because the 2 norm is only 0.3288, while the F norm it have a distance of 0.9379. So that means the H2 norm will give you a good normal because it will get a solution which is close to the solution of the original problem. Actually, you can see, the gradient and the second order derivative, the Hessian of the quadratic model, also you can prove the H2 norm minimization will get a much better approximation point. Even we can study the interpolation order errors, how it going on as the iteration go on. Of course, the first initial 5 points, you have interpolation. But when the iteration going on, then we can compute the error of the model to the original function. Then we can show you Powell's model, which is plotted in red, and our model, the H2 normal, is plotted in red. In blue, you can see the blue line is in general is lower than the red line. That is more accurate. So for the numerical results, we not only compare with the Powell's algorithm. As I said, the Powell's algorithm is least F norm update. We'll also compare with the DFO, which is the algorithm suggested by Andy Cohn, Katia Scheinberg, and also Louis Vincent. They are trying to minimize the least Hessian matrices of the quadratic model. And we also compare not other type of method, not only model-based, like simplex method, and also find the difference BFGS, because BFGS is, the famous method for using gradient. So we just converted the gradient method, replace the gradient by finite difference to compare. So the test problem we have run is 50 of them. Many of these problems are from the QTR, which is very famous for people doing optimization algorithm comparison. And some are from Hawk and Shutkowski's book. So that is, anyhow, those problems are classical test problem for optimization. This is the result of the compare about the algorithm, our algorithm to the other algorithm. So I have to explain to you why this plot mean. That is called the performance profile. Basically, the curve at the plot is the proportion of problem particularly solve, which can get the solution of the problem within the number of iteration of the best solver. So for example, look at, alpha equal to 2. So that means how many problems we can solve at most 2 times of the first algorithm. That means the line is higher, you can solve more problems, the algorithm is better. So you can see in generally our algorithm, which is plotted, the dotted line in red, which is the best one. Of course, in some section, you can see Powell's method is also so good. That means particularly when alpha equal to between 1.3 to 2, Powell's algorithm is good. That means Powell's algorithm is really very stable. But you can see our algorithm is definitely good, particularly for big alpha. This is really showing you, even though it's a simple idea to improve Powell's update, but really get a good result. That is the final slide of my talk. So I hope in nearly 45 minutes, I have shown you, this F-norm updating quadratic model of Powell is really a very good technique for delivery optimization. But we're proposing a this H2 norm updating quadratic model, which performs better than Powell's algorithm and also outperform many of the classical state-of-the-art algorithm. For doing this, of course, we make our algorithm efficient. We have to get a fast inverse matrices of the KKT system, fast updating to get the inverse of the KKT matrices. We also make our algorithm stable, trying to maximize the denominator in the updating formula to make the algorithm more stable. That is really, our numerical results also showing our algorithm is very efficient. And also, I have to admit, this is ongoing work. We are still a lot of things to do. For example, even though I have claimed our algorithm looks very likely will be reduced the accuracy of our approximation, but that is not a strict mathematical proof. So we still need a very rigid, convergence analysis, to show you how our algorithm will converge to the minimize of the solution. Even though, computationally, all the results we show in our algorithm are converging to all the problems. Another thing I think maybe we need to study is how we can generalize our technique. At the moment, I use the 3 terms, add them together. But maybe in the future, we have to explore, have weighted norm of them. And of course, we can also study different model, not only quadratic model, but also other non-quadratic and even though other type of model. So that's the end of my talk. Thank you very much. Professor Pani, thank you very much.
Thanks a lot. So, any suggestions or questions? First, let me ask people who are online. Those who are online, you have any suggestions and questions?
What is the question? I cannot hear clearly.
No, I am just asking the people who are online whether they have any question.
Okay. Are there any people online want to ask a question? Okay, sorry. I thought that you're asking me a question. Okay. Are there one online want to ask a question or not?
Oh,
Online people will have to raise their hand in order to
Are there any questions? I cannot hear.
yeah. So let me ask the audience here, which are offline. Any question? No.
It's a nice talk, Professor Yuan.
Thank you.
A couple of questions. The first one is, at some point you assumed f is in C3 omega. The function is in C3 omega in one of the results.
Yeah.
And the example which followed was not C3. So is it a theoretical requirement? I didn't follow there.
That is a very good question. Actually, the theoretical analysis I use is about the omega, which is a fixed region. So as long as you have any kind of fixed convex set of an omega, all the theory can go on. But in practice, in the algorithm, because in the real computation, I have a trust region. The trust region is moving, so it's changing from iteration to iteration. That is why I say at the moment we don't have a conversion result for the algorithm, because the theoretical is for fixed region, but in computation, the algorithm is actually behavior, it have a moving target. So that is difficult. Very good question. Thank you very much.
Thank you. My second question is more general. I want to know, how do we connect this to this automatic differentiation? By Grievang's school. Automatic differentiation, where they don't compute derivatives.
You mean automatic
Difference.
Oh, yeah. That is, automatic differentiation is also a good technique for in some of the algorithm implementation. Is if you know the function value is computed by some kind of computer program, then the automatic differentiation, mainly by Andrew Grievang, who is in German. So he have a technique, then you can decode the algorithm for solving to compute the function value, then automatically you can go to the gradient. So in this way, many of the problem, if you have a subroutine can compute the function value, you can automatically get the gradient more or less at the same cost of the computation. That means you can using fancy algorithm like a BFGS, all the gradient method. But of course, for some type of method problem, you can use automatic differentiation. If you can do, of course, I encourage you to do. But for delete-free optimization method, we'll really think about the problem where the function value is computed, not by analytical function sometimes. So that means automatic differentiation cannot apply to this kind of problem. For example, integrated circuit design, for example, some kind of electronic company, he gave you a chip and you input some parameter, then you get output, then you don't know what is the function. And also some kind of like a machine learning or neural network, he generalized, you know, like a mobile phone, you get some, you turn the antenna, you can get the signal, but you don't know the mathematical formula for the function, something like that. Then the delete-free optimization do have it is low. But of course, you're right. For a large class of problem, automatic differentiation can play a very important role. Thank you very much.
Thank you. And I would also like to use this opportunity. The audience here may not know you were one of the first persons who started off with the BRICS Math Conference. The idea was started. So thank you very much for this. Doing this math conferences. Thank you.
Thank you very much. Thank you. Thank you.
So any other question? Okay, so let us thank Yuan once more.
Thank you very much. Thank you very much. Bye-bye, and hope to visit India in the future. Thank you.
Surely.